So let's see, any of you have any questions about this particular topic? Yes.
So since you mentioned one of your assumptions is that it'll take k steps before a thread gives up the lock, do you use any kind of back-off time in the scheduler to control when another thread will request that lock?
You mean it will take k steps to release the lock or scheduler?
The scheduler.
Oh,
yeah.
No, we didn't reason at that level at this moment. I anticipate that in a real-time setting, if you use ticket lock, then you really have to be implementing the ticket lock in a way so that there's some time bound you can put on this. Yeah. By the way, I want to tell you, majority of today's real-time OS kernel simply use spin lock. They don't really do this kind of reasoning.
Right.
But I thought we were cool because we can do this kind of reasoning. We have at least the hope, to do that. But it's not very rewarding research because the hardware does not provide a very good cost model for these machines. So if I spend many months to reason about that, the reviewer will still say this is garbage because the real machine does not behave like that, and so it's hard work. But so we will have to think about. So this is the problem of working on real-time OS because the hardware is so bad they don't give you any guarantee about the cache behavior, memory behavior, and so on. We spend a lot of time doing verification. We think we make a good progress. People will still say, yeah, so what? The machine does not behave like what you want. But, we are doing science. You cannot just beat down other people's paper. This forces my students all go to work on blockchain because the cost model there is man-made, like how much resource each instruction cost. Every load instruction costs 1 penny or what. And it's regardless whether it hit cache or not. So, right.
Does your proof proceed along the lines, basically, that the system has a winning strategy against these environmental adversaries? Is that the rough idea?
No. So the so-called winning and so on is so whenever we say we use game semantics, it's not like directly copying it. It's just the idea is similar. So winning strategy and so on is often used to describe a certain kind of safety property of these things. We are kind of already proving the safety of the programs. So so the strategy here is used to serve as a compositional mechanism. We are clearly always composing safe strategies. Unsafe strategy is something we want to rule out. So there's a similarity, but the game semantics was mostly developed to reason about the full abstraction of sequential programs. Not much about concurrent programs. There are some work on concurrent strategy, but I would say the usage scenario is a little bit different, and the people seldom do the kind of a refinement of a strategy like what we do here. So. So we could have invented a new name for what we do, but we really believe it's like a strategy. And that's how I related to linear logic and the game semantics for strategy, because the underlying idea is every little programming language feature, if you really want to understand it, it's a full abstract spec, or what we call deep spec. You only see what's observable at the boundary with the rest of the environment. It's just the environment here is much richer than the traditional game semantics in a sequential PCF-like language, which is very idiomatic for that setting, right? Yeah.
So could you clarify where exactly linear logic comes into your proofs or your reasoning? So why I believe Girard, right? It's not because he's Girard, he invented the system F. I just believe him, right? I mean, I have spent 30 years of my career
believing in too many Turing Award winners world and believing in too many and made lots of sacrifice for believing that because I spent many years of my career to work on some stupid problems. And so I don't believe Girard. But there is a good reason why linear logic, Girard is trying to say that we are looking for the model for computable functions, okay? And if you want to define computable functions, you actually need to model things that can be implemented using reasonable control of a resource with a computable engine, which is what small step abstract machine try to accomplish for you. And so linear logic is really, so the way we understand the linear logic is not to try to see, oh, it's used to control resource or anything, but it's really because it basically says if you go to look for literature on game semantics for linear logic, they will tell you, oh, every little thing inside linear logic is a game. And the game means, I'm going to play something, if I'm a linear type integer, you ask me for a value, I will return you an integer value. And if you have a tensor product of int cross int, you might ask me for the first field, you might ask me for the second field, but the point is, the game of a tensor product of two games is how you interact with this particular data structures. And so it is really, having the concurrency as the very basic connecting primitive. What's really cool about linear logic is the negation has very simple semantics. The negation of a type, or a predicate is just the due, like if you are the player's view of a type, and the negation is just the opponent's view. And this is just how simple the negation is. And if you go to classical logic, negation is super complex. You have to understand what is a continuation. And the reason why that's so hard is because it's a sequential language. Anytime you want to understand something's negation, you have to say, oh, I have to capture continuation somewhere, then jump back to it. Who understands cos-EC, right? Your mother, father clearly does not. I spent my whole PhD thesis work on cos-EC. I know it, but it's not something that is easily understandable. And not, all these lambda calculus, intuitionist logic is really, way off the thing because they don't even know how to model negations, right? And without negation, you cannot really give a very compositional semantics of the basic function type, which is why these linear logic, they really give equal treatment of the negative value and the positive values.
So speaking of negation, you mentioned rely guarantee. The talk yesterday mentioned rely guarantee.
Yeah.
Do you see a scope for incorporating deny guarantee reasoning?
I think it's relevant, but it's too specialized. Deny guarantee is designed for these fork join-based concurrency. I guess it could be possible. You have to realize we do all these concurrent reasoning, and I spent 10 years working on concurrent separation logic and the rely guarantees. We don't exactly use the thing we developed there. We have to develop, these refinement-based proofs, which is a rely guarantee-based, but the underlying mechanism is different from the separation logic setup. Okay, because they are the only reason about the safety. They don't reason about the trace, and so we are really going much richer than what we are doing there. Yes.
Hi. You mentioned at some point that there's a hesitation to add a lot of ghost state in these proofs, and basically that you're advocating not worrying so much about that and adding ghost state to make the proofs easier. Is that hesitation on the part of other proof efforts?
It's because if you define your program logic, I think you are going to see more about verifiable C, right, and so on. I think they are now very aggressive adding ghost state too. But when you're designing a program logic of an existing programming language, you follow the pre-post condition mechanism. Ghost state is, still known as a ghost state. So you will be a little bit hesitant because you have to worry, whether it's too many. But if you have an abstraction layer, you will be adding a lot of ghost state. You could then hide it at the next layer, and then you add a little bit more. So you can be much more aggressive in that sense.
So I guess my question is, how come other proof methods are hesitant to add it? Is it because there's an implication there's more work at the end to prove that the ghost state doesn't actually influence the execution?
The reason why it's hesitant is because the support for ghost state is not always that good. They can add it, they cannot easily hide it. You can abstract over it, you cannot hide the existence of it, where in our case, we can actually add it, then hide it at the next level.
At the level up?
Yeah, at the level up, yeah. Well, it's a question for those peoples, I mean, yeah.
My understanding was that if you add ghost state, then you then have to prove that nothing is, that the actual behavior of the system is not dependent on the ghost state. So I'm not sure if I'm misunderstanding.
We don't have to prove that, because we are doing these layer things, and every ghost state must be supported by an underlay that provides the implementation. Okay? So our use of abstract state is not really the same as the traditional notion of a ghost state. It's abstraction layer based. Okay? Any more questions? We really already used up our time, so if you guys have more questions, feel free to ask or come to talk to me offline. All right? Okay, that's it.